All right, here in Unit 2, we're going to peek in on some acid-base chemistry. This unit is entitled Chemical Reactions. Acid-base reactions are definitely a huge part of chemistry. We will spend much more time on these second semester, but it's important to look in on them, refresh your memory a little bit, and it'll be a nice foundation for us later. But these acids and bases, our first definition of them came from Mr. Arrhenius back in the day, and he said acids, when dissolved in water, produce hydrogen ions. Bases, when dissolved in water, produce hydroxide ions. This definition pretty much said that the acids have the hydrogen ion in them and donate them into the solution. Bases have the hydroxide ions in them and donate them to the solution when they're dissolved. So this is a very limited definition because we know nowadays that there are acids and bases that do not have hydrogen ions or hydroxide ions, but yet they still have acid and base properties. So the evolution of this theory turned into the Bronsted-Lowry theory. The Bronsted-Lowry theory looks at acids and bases through a proton transfer reaction. Acids donate protons, hydrogen ions. Bases accept the protons, hydrogen ions. And so here we see two examples of this. The nitric acid, still an acid, it was an acid under Arrhenius, still an acid here. It donates its hydrogen ion to the water. And so on the other side you see hydronium, which is often abbreviated H+, and you see the nitrate ion. And so what we see is that through that proton transfer, nitric acid is acting indeed as an acid. Now, just as a side note here, we will study this more in depth later. This reaction can also go the other way. There's what we call these Bronsted-Lowry conjugate acid-base pairs. Because in this solution, there's no stopping hydronium from donating the hydrogen back to nitrate so that it turns back into nitric acid and water. So again, we will look at those pairs and all that stuff a little more in depth second semester, but it's just nice to point out here. Now ammonia, NH3, it's a base. It has basic properties. It does not have a hydroxide in it. So you can see here what's going on is that a hydrogen ion is being transferred from the water to the NH3, and you create NH4+, and there's the hydroxide. You'll also notice now, water accepted a hydrogen ion, donated a hydrogen ion. Water has that crazy ability to do both. It's a substance, we call it amphoteric, when it can act as both an acid and a base, donating and accepting a hydrogen ion. And again, we'll study water and its self-ionization and the ion product constant of water in second semester. But right now, you see here the more currently accepted definition of acids and bases through Bronsted-Lowry. There's also a Lewis definition where we talk about lone pair electron donations and accepting, but we'll briefly talk about that at a later time. A big concept here, though, and you kind of need to start remembering, is the difference between strong and weak. A strong acid or base ionizes completely in water, and it's what we call a strong electrolyte, like we saw the other day in the classroom. Conducts electricity very well. Hydrochloric acid, when put into water, completely ionizes. Hydrogen ions and chloride ions. The hydrogen ions, again, typically showing up as hydroniums. Sodium hydroxide, when you put pellets of sodium hydroxide into water, it completely breaks apart into sodium and hydroxide ions. The nice thing is, there's really just 6 strong acids and 6 strong bases that AP would like you to remember, and it will definitely help you. This is one of those things when you're taking your test, I tell kids to write those down really quick on your information packet so you don't forget them. Your 6 strong acids, 3 of them come from the halogen family: hydrochloric, hydrobromic, hydroiodic. Then we've got perchloric acid, nitric acid, and then H2SO4, sulfuric acid. So you should definitely know those 6, and you should know your 6 strong bases. From the alkali metals, we've got lithium, sodium, and potassium hydroxide. And from the alkaline earth metal family, we've got calcium, strontium, and barium hydroxide. Once you know all those, fantastic. All the rest of the acids and bases are considered weak. And so that's the nice thing about only having to memorize those 12 things. A weak acid or base only partially ionizes, and they are a weak electrolyte. So yes, ammonia and water interact and we get ammonium and hydroxide, but not to a very great extent. When we write weak acid-base reactions, we definitely want to show a double arrow. Strong acid-base reactions, we typically just show the one forward arrow because it completely ionizes. So we definitely want to pay attention to that. Some of these, like acetic acid or this hydrofluoric acid, we're talking like 1% or anywhere between 1 and 3% that actually ionizes and creates the acidic solution, so, or basic solution. So it's not to a very great extent. And again, we'll study that more in depth later. But here's kind of like a little picture. So over here on the left, strong acid, it completely breaks apart. So HA, a typical symbol for strong acid or acid, it breaks apart completely. All the H's and A's are separated. So that would be like hydrochloric acid. Over here, it shows a weak acid. I don't like how they use the B symbol, but we'll live with it because it's a decent picture. But here you see HBs. Let's call it hydrofluoric acid. On the other side, you see one fluoride and one hydrogen, and then all the rest are still intact. So there's just a tiny little bit of dissociation. That's the difference between strong and weak. Over here, everything is dissociated. The weak, not so much. Now, a very common occurrence when we mix acids and bases together, we get some neutralization. So here we see when a strong acid is mixed with a strong base, we create a salt and water. Okay, the neutralization reaction produces this water. So again, if we are looking at the net ionic equation of what's going on, the hydrogen and chloride break apart, the calciums and hydroxides break apart, the calcium and chlorides break apart, the liquid water stays together. So from a net perspective, calciums are gone, the two chlorides are gone, and so we end up just having hydrogen ion plus hydroxide ion makes water. That's the truth for every strong acid mixed with a strong base. That's always going to be your net ionic equation. Here we see a weak acid. How do I know HCN is weak? Because it's not one of the 6 strong acids that I've memorized. And we see it interacting with potassium hydroxide, a strong base. So the net ionic here, HCN, since it's weak, is going to stay together. Potassium hydroxide breaks apart because it's strong. Potassium cyanide is a soluble salt, all potassium salts, and then water again stays together. So here we see our net ionic equation shows that the HCN is still predominantly together. There is an exception, the ammonia exception. There is a neutralization effect that occurs when we have this reaction here. Strong sulfuric acid reacts with weak ammonia, and you create this ammonium sulfate. But when you get down to the net ionic, because the sulfuric acid breaks apart, ammonia stays together, all ammonium salts are soluble, sulfates go away, and we end up with hydrogen ions plus ammonia. Makes a very, very stable ammonium ion. And so that's the driving force of this reaction, is that NH4 plus is very, very stable. So that's just a small exception. It's not very much tested on the AP exam, but it's important to know because we like knowing all about chemistry. Last little pieces parts. probably can tell, but when you look at these formulas for acids, monoprotic acids, they just have one hydrogen in their formula. All right. And there are, again, our 6 strong acids plus a bonus one. And then polyprotic means that they're going to have more than one. Sorry, I don't like making incorrect statements. 2 are not strong. 2 are not strong. Here's our other strong acid. Our only polyprotic strong acid is H2SO4. What's interesting here is when you've got your polyprotic acids, for example, phosphoric acid, when you mix it with base, it depends on how much base you mix it with to see what reaction is going to happen. There's still a neutralization effect going on, but what we end up creating are what's called acid salts. These salts are called acid salts because they still have hydrogens in them that can be considered acidic. Now, when you get down to the sodium phosphate, no, there's no more hydrogens anymore. If you add enough base to the phosphoric acid, then you do not create the acid salt. Last thing, there are definitely some acid-base reactions that produce gases. The ones we'll focus on here is when you have compounds of carbonates, sulfites, or sulfides, you will create carbon dioxide, sulfur dioxide, or hydrogen sulfide gas when those salts mix with acid. All right, so when I look here, sorry, I didn't mean to take that away. If sodium carbonate mixes with hydrochloric acid, you get sodium chloride, water, and carbon dioxide gas. Now, I highlight this reaction because when you look at it, you're like, wait a second, sodium carbonate plus hydrochloric acid, I can see I get sodium chloride, but I thought I should get the hydrogens and the carbonates, and I should make carbonic acid. True, but carbonic acid in solution notoriously breaks apart into carbon dioxide gas and water. So that's just something we're going to have to recognize, and through some labs and activities, we'll get better at that. But again, just knowing that these 3 types of ionic compounds, carbonates, sulfites, and sulfides, create gases when mixed with acid. Last thing here, the net ionic of this equation. Okay, sodium carbonate breaks apart, hydrochloric is strong, breaks apart, sodium chloride breaks apart. So we can say bye to the sodiums, we can say bye to the chlorides, and we end up with carbonate ion plus 2 hydrogen ions making my liquid water and carbon dioxide gas. We're going to spend time in class going over this and examples, so if it was a little confusing to follow along, bear with me. Also, we're going to spend a lot more time next semester on acids and bases. They're very important in chemistry. Some of the more common reactions that you see in everyday life as well. So we will definitely have our time spent with them later. All right, see you soon.